What is antimatter? What happens if matter and antimatter interact? How was antimatter discovered? Why don't we usually come across antimatter in our daily lives? All these questions and many more come to one's mind when thinking about antimatter. But first things first, let us define and understand what antimatter is. Some of these quantum numbers are the lepton number, one for the electron and each of the other 5 members of lepton family, and the baryon number, 1/3 for each of the 6 quarks that make up the baryon family. Antiparticles are expected to interact with other antiparticles in exactly the same way ordinary particles interact with each other. The laws of physics are almost symmetric when it comes to matter and antimatter. In fact, a universe made up of antimatter would be indistinguishable from ours. Going into a little bit more detail, the anti-electron is called a positron for positive electron, and it is positively charged with a lepton number of -1. The positron has exactly the same mass as the proton. The proton is a positively charged subatomic particle made up of 3 quarks, giving it a baryon number of 1. Its antiparticle, the antiproton, has the same mass as the proton, but it is negatively charged with a baryon number of -1. -1/3 contributed from each of the 3 antiquarks that make up the antiproton. Neutral subatomic particles, such as neutrons, are interesting. The antineutron has the same mass and 0 charge as the neutron, but it will have a baryon number of -1. Again, -1/3 coming from each of the 3 antiquarks that make up the antineutron. So what happens when matter and antimatter interact? The answer is fireworks. When a positron interacts with an electron, they both annihilate to produce 2 X-ray energy photons. So we are in luck that antimatter is so scarce in the universe nowadays. Otherwise, we would have been burned by X-rays and gamma rays every time matter and antimatter interacted. As a matter of fact, if you were to meet your anti-self, then both of you would annihilate and release the equivalent energy of roughly 2,500 megatons, almost 1/3 the total energy of the world's arsenal of nuclear weapons. Antimatter could sure make a mighty powerful spaceship engine, if you can find a way to produce macroscopic amounts of antimatter and a way to store it in isolation. Some modern particle accelerators regularly produce antiprotons for use in high-energy physics experiments. Now that we know what antimatter is, let us see how physicists discovered it. Back in the year 1928, Paul Dirac, one of the founding fathers of the new science of quantum mechanics, was trying to solve an equation that included the effects of the theory of special relativity to describe the behavior of electrons in the microscopic world. To his surprise, the equation admitted solutions that corresponded to electrons with negative energy going back in time. Any insecure student of physics would have blushed with embarrassment and redid the math. However, Dirac was sure of his math. Instead, he reinterpreted his problematic solution to denote an anti-electron with positive energy going forward in time. 4 years later, an experimental physicist by the name of Carl Anderson proved Dirac right by actually observing the anti-electron, the positron. The discovery of the positron earned Anderson the Nobel Prize in 1936. Dirac had already won the Nobel in 1933 for his contributions to atomic physics. Are you wondering where Anderson's positrons came from? The positrons that Anderson discovered originated in atmospheric showers of subatomic particles that result when very high-energy cosmic rays, mostly protons, interact with atoms in Earth's atmosphere. The story of the prediction and subsequent discovery of the positron is instructive and shows how big discoveries in physics are often made. The device used by Anderson is called a cloud chamber and was a standard instrument used in nuclear physics labs at the time. A particle going through a cloud chamber would leave sort of a trail of bubbles in its wake. Applying a known magnetic field would curve the particle according to its charge. The positron in Anderson's cloud chambers curved in exactly the same way as electrons, but in the opposite direction. As a matter of fact, these oppositely curving tracks were observed several years before Anderson at around the time of Dirac's prediction, but none of the physicists who observed them pushed the issue further. It was Anderson who persisted and tested and retested his results, and thus confirmed the reality of the positron. This is in a way similar to Dirac when he came across his negative energy electrons. He did not simply brush the solutions aside as a mathematical curiosity, but instead reinterpreted them in a way that made us discover a completely new side to the universe. You can discover other sides of our universe on our YouTube channel. But let us continue with the story of antimatter. The reason that antimatter is rare in today's universe is that antimatter is created by very rare nuclear reactions that produce very small amounts of it. The antimatter that we get from this is mostly at the subatomic level. Positrons, antiprotons, antineutrons, and antimesons. Mesons are the protons and neutrons' lighter cousins that are made up of a quark and antiquark. Yes, physicists have created and studied antihydrogen, but that was under very difficult laboratory conditions that required complete isolation of the antihydrogen atoms so that they don't interact with the walls of their container and annihilate in a jet of gamma rays. Right now you're probably wondering if antimatter has any useful purpose at all, apart from allowing physicists to learn more about the universe. The answer is yes. Every time a patient undergoes a so-called PET scan to detect tumors in the body, antimatter is involved. PET is an acronym for positron emission tomography. The patient is injected with radioactive sugars that accumulate at tumor sites. These radioactive sugars then gradually decay, emitting positrons in the process. A specialized and highly sophisticated instrument then maps out the locations from which the positrons are emanating, thereby giving a highly detailed view inside the human body. Patients who have had PET scans remain radioactive for a few days and are usually advised to stay away from children and pregnant women, given the risks posed by radiation to children and fetuses. Okay, so we now know what antimatter is. We know how it interacts with matter. We know how to produce it here on Earth and how it is produced in nature, basically under very special conditions and in very small amounts, and that it exists for a very short period of time because it interacts quickly with ordinary matter. But what we still don't know yet is why all stuff in the universe, planets, stars, galaxies, are predominantly not antimatter. This issue is so important in physics that it even has its own name, the matter-antimatter asymmetry problem. Addressing this issue requires that we delve into cosmology and high-energy physics known as particle physics. Full disclosure, the solution to the above problem is still being worked out by physicists as we speak. Nevertheless, we will try to get a very simplified version of the known parts of the answer. The theoretical framework within which to understand the matter-antimatter asymmetry is three-pronged and was formulated over 50 years ago by physicist Andrei Sakharov. Our quest begins right at the beginning, the Big Bang. The Big Bang is the instant when our universe was born. The Big Bang created equal amounts of matter and antimatter. For every electron there was a positron. For every quark there was an antiquark. Mind you, protons and neutrons formed much later. They formed a few minutes after the Big Bang, at which time almost all antimatter had disappeared. But we are getting ahead of ourselves here. Let's go back to the Big Bang. During the first fraction of a second after the Big Bang, the universe was an extremely hot soup of particles and antiparticles and intense radiation. Particles and antiparticles annihilated each other to produce highly energetic photons, and the energetic photons could interact with each other to produce again particle-antiparticle pairs, all happening under the watchful eyes of the laws of particle physics. The universe would have remained in this fiery thermal equilibrium for eons without anything interesting happening had it not been for an astounding cosmological fact. The first prong. The universe is expanding. The expansion of the universe led to cooling. The energy of radiation decreased to a point where photon interactions were no longer energetic enough to produce particle-antiparticle pairs. The result is that the refueling of the abundance of the pairs stopped. If no other processes had interfered, The particles and antiparticles would have annihilated each other with time, and we would have been left with a universe filled with only photons and no matter or antimatter at all. We wouldn't be here to discuss it. The effect of the expansion of the universe is to stop the particle-antiparticle pairs from being replenished. Now, other high-energy physics processes must come into play to produce the matter-antimatter asymmetry, which brings us to the second prong. If you recall, antiparticles have the opposite baryon number to particles. High-energy physics reactions have to conserve energy, momentum, charge, lepton number, and baryon number. A quantity is said to be conserved if its value before the reaction is the same as after the reaction. All the laws of high-energy physics require that the above-mentioned quantities be strictly conserved, or so it seems. The very absence of antimatter in the universe requires that the conservation of baryon number must be violated to some extent under certain conditions in order to produce the matter-antimatter asymmetry observed in today's universe. To what extent? To about 1 part in 1 billion. How do we know that? Astrophysicists know that there are roughly 1 billion photons for every particle in the universe. This means that for every 1,000,001 particles that there were only 1 billion antiparticles out there. The billion particles will annihilate with the billion antiparticles, leading roughly to 1 billion photons, with the upshot being that when all is said and done, we will have 1 particle and 1 billion photons, the particle-to-photon ratio observed by astrophysicists. However, there is no evidence yet in particle physics labs of the violation of baryon number conservation. Moreover, there is no theoretical process within the accepted paradigm of particle physics, the standard model in which the baryon number is not conserved. Evidently, gaining a full understanding the matter-antimatter asymmetry requires new physics. The third prong needed to understand the matter-antimatter asymmetry is the so-called CP violation. The laws of physics, including conservation laws, should be the same if you were to change the signs of the charges. C of all the particles involved in a reaction and look at the reaction through a mirror, P parity. CP violation occurs when the outcomes of a reaction change upon inverting the sign of the charges and taking the mirror image of the reaction. CP violation is needed to produce more particles than antiparticles in the very early universe. Glimpses of CP violations have been observed in particle physics labs since the 1980s in reactions involving K-mesons, referred to as kaons, and other subatomic particles. However, the amount of detected violation is not enough to explain the full magnitude of the matter-antimatter asymmetry. Naturally, more experiments are still needed.